So, in the last session, we discussed about the star connected source and various terminology which are phase quantities and line quantities. So, let me quickly show those diagrams once again. First, you should understand this basic diagram very clearly that so the source is connected in star or Y connection. So, how they formed this three phase source is that we considered three individual single phase AC generators. We connected one end of these sources as together called as neutral or common terminal. Remaining three terminals of each of these individual single phase generators are brought out, which we are calling as R, Y, B terminals of the three phase generators. And now, if we see the basic idea that power transmission or distribution, the generator terminals will be extended over a long length. So, those lines of conductors, this portion of the things, lines of the conductors which are there on the towers or on the poles, we will call as a lines. We will call as a lines. And here, whatever referred among these lines can be called as line quantities. So whatever there inside of this generator can be called as a phase quantities. For example, the individual corresponding thing to this R phase or coil 1 voltage is ER, so whose current produced by this single phase generator is IR. So these two can be called as phase quantities, which are phase voltage ER, phase current IR. Similarly, phase voltage EY, phase current IY, phase voltage EB, and phase current IB. So in this way, inside of this, the quantities are referred as phase quantities. Now once we come to the lines, the flow of current through this line is equal to line current. So that may be IYL, IRL, etc. All these currents which we shown in the last session. And the phase voltages are line voltages are like between any two lines. It can be as R phase to Y phase line, and Y phase to B phase line, and B phase to R phase line, which we represented as ERY, EYB, EBR. So like this we had shown. And here the neutral terminal we will not call as a single phase generator line, it is common line, so that we are not referring as a line to line voltage. And here we had shown that phase quantities, any single phase coil induced voltage can be referred as a phase voltage. So we had shown some notation, that is R2N, Y2N, B2N, or referred as a phase voltages. And phase currents are current produced by these individual coils, which are IR, IY, and IB. Similarly, line currents are flowing in the lines of the system, so which are IRL is equal to IR, IYL is equal to IY. Here in the Y configuration, we could see that the line quantities are equal to phase quantities only for currents, not for voltage. That you should carefully observe. The currents only for currents, not for voltage. The line current is equal to phase current. This is true for always Y configuration. Whereas the line voltages are the voltage between any two lines of the generator, which may be R2Y, Y2B, or B2R. And for deriving these unknown line voltages, we must start from some reference. So in which here in three-phase system, little more description about the system is required. One is balanced, another is a sequence of the voltages. Is it positive sequence or negative sequence? If we know these two, we can quickly make something conclusions. We can derive each of the phase voltages in this way. So for example, ER is equal to E at an angle of 0. I am considering magnitude is E and angle is 0. If it is balanced, the next corresponding phase voltage also must be equal, E. Similarly, if it is balanced, the angle of the next phase must be lagging this voltage by 120 degrees, and next phase further must be lagged by this y phase by 120 degrees. Thereby we get minus 240, or it can also be said as leading by plus 120 degrees. So either of the way we can refer. If we know the phase sequence, we would have written like this. If phase sequence is opposite, then it may be like this. So after y, after R phase, if it is negative phase sequence, what we get? B phase we get. So EB is equal to E magnitude is E at an angle of minus 120 degrees, at an angle of minus 120 degrees, and EY is equal to E at an angle of minus 240. Remember that this is for negative phase sequence, or RBY phase sequence, RBY phase sequence, which is negative phase sequence, negative phase sequence. So try to understand the things clearly, like, so these are helpful in solving the problems most of the times. This is just as extra information. And once we know these phase voltages, now we can write up the KVL for various loops, whichever we are considering as like this. So as an example, I had shown you this, like between R phase to Y phase. ERY is the line voltage. Then this can be written as phasor sum of ER minus EY. So if we substitute those things, we got this as root 3 times of the phase voltage, and angle is 30 degrees. And I had shown the phasor diagram. I hope everybody worked out on this phasor diagram. From the phase voltages of this R, Y and B, so first you can take up negative voltages of all these things, which is at 180 degrees, which is in phase opposition. Like R is here ER, Y is here EY, and B is here minus EB. Like that, then you add up those ER and minus EY, you will get ERY. Try to observe that this line voltage is leading the phase voltage by 30 degrees. So let me write that point. This is very important. So today is 16th. So let me write. This is common conclusion that from the previous session, the observations are. So let me write in this way. Line voltages lead the lead the let me write more precisely. Corresponding corresponding phase voltages phase voltages phase voltages by an angle 30 degrees. This is very very important statement. From this we can put up many things in this way. So for example, as like this, let me take up R phase here, let me take up Y phase here, and B phase here. This is RYB. I am not writing EREYEB. You should understand this. Now if we know this phase voltage, let us say ER. Now I can write its corresponding line voltage as like this. This is at 0, let us say. This is at 0. This is at minus 120. This is at plus 120. Leading in the sense that it should be in the forward direction. Forward here is anti-clockwise direction. This is positive angle direction. Positive angles. Leading in the sense that that corresponding voltage should be in the forward direction. that what we call as leading voltage direction or positive angle direction. That is one thing. Once we know the phase voltages, now I can produce from this conclusion the line voltage as like this. The line voltage magnitude must be, the line voltage magnitude must be root 3 times of the phase voltage. So the length of this should be little bigger than phase voltage, that is ER, and the angle of this should be in the positive, like in the forward, by an angle of 30 degrees, by an angle of 30 degrees. So this is 30 degrees. This is what E R, we considered reference as R, then R, after R phase, what phase we will get? Y phase. So it is positive sequence. So I am taking the next corresponding thing is Y, ERY. So in this way, directly I can produce the line voltage once we know the phase voltage. Phase voltage magnitude we know, phase voltage angle we know. So we can get the line voltage. Similarly, you can take up this Y phase corresponding thing. For if we sit over here, what is the forward direction? What is the positive angle direction? Anti-clockwise. So that means in this way. That means now your line voltage should be little leading by this phase voltage, and the length of this phasor should be little bigger than the y phase voltage. So now angle made by this will be 30 degrees, 30 degrees. That's what I said, corresponding phase voltage. Now what is this voltage? Is that y. Next, after y, what kind of voltage? Means if it is phase sequence is ryb, something like this. This is r, this is y, this is b. Then make some circle like this. Then after r we got y. Then after y we got b. So the here, so y to b voltage, y to b line voltage. So magnitude is how much? Root 3 times of phase voltage. What is the phase voltage? EY. So always remember, take up or concentrate on this first letter, that is y. Here first letter is r. So these are important. Now here your voltage is equal to root 3 times of your first corresponding thing voltage. However, it is a balanced, so in balanced case all are equal, so no issue. Similarly, you can think of for this position, if somebody is sitting over here, what is the forward direction? It is anti-clockwise. So where you should have this line voltage. Line voltage length should be little bigger than the phase voltage, one thing. And other thing is that this should lead the phase voltage by an angle. This should lead the phase voltage by an angle 30 degrees. 30 degrees. Now what is this voltage? Can you tell me? If we know phase voltages, I could produce the line voltages in this fashion. Can you tell me what is this line voltage? EBR. Very good. EBR. And how much is this length of the magnitude? This magnitude length is root 3 times of EB. EB. The first corresponding suffix, that is EB. So in this way you can produce the line voltages if we know the phase voltages. Similarly, if we know line voltages, we should be in a position to produce the phase voltages also. That should be in this way. If I know this line voltage, then phase voltage should lag the line voltage by an angle 30 degrees. So it is simple there. So these like flexibility of handling all these quantities will come through the practice of the numerical problems. So that you should work out. So I had given the concept, so you should work out on the numerical problems. So anyhow, we discuss some more problems on the three phase systems also. Right. So this is the phasor diagram which we had seen in the last session. This phasor diagram is very important, which relates the line and phase voltage relationship. Whereas the line and phase currents for star is a simple, line current is equal to phase current, no issue at all. But phase voltages are different. So how it is different is that, let me write here conclusion that So R Y line voltage is equal to root 3 times of ER at an angle of 30 degrees. At an angle of 30 degrees. Similarly, E E E YB is equal to root 3 times of, so what we got, root 3 times of EY, root 3 times of EY is nothing but E, and angle is minus 90 degrees. Angle is minus 90 degrees. How we get is in this way. So just let me put up here for your understanding how we got that minus 90 is EY phasor into 1 at an angle of 30 degrees basically. For this phase voltage, it is multiplied by 1 at an angle 30 degrees. That means this line voltage is leading this phase voltage by this 30 degrees. That is the importance of this terminal, this term. So now let me put up this thing little further away. Just I am giving extra information here that EY at an angle of minus 120 degrees into 1 at an angle of 30 degrees. So if you multiply this, so you will get root 3 EY at an angle of minus 90 degrees. Similarly, EBR is equal to root 3 times of EB at an angle of, that is 30 plus 120 or minus 240 plus 30. In either of the way you can write. So 30 plus 120 is 150. So in this way you can get the line voltages, and here try to observe that the relation between the phase and line as like this. So this is the line voltage magnitude, which is root 3 times of the phase voltage. Here also root 3 times of the phase voltage. Here also root 3 times of phase voltage. Now the general conclusion is that I will write like this. EL is the line voltage. EL is equal to root 3 times of EP phase voltage. This is the general conclusion. These are magnitudes only, try to observe carefully. These are magnitudes. I am not giving angle information here. You should understand that angles are lead the phase voltage by 30 degrees. Or sometimes we may use this relationship also. Phase voltage is equal to line voltage divided by root 3. So we may use either of these relationship, which are very important. Okay. Right. So now let me move on to the other part of this diagram. This diagram. So let me take this diagram once, or I will take the plane diagram. Somewhere I had drawn, I think. No. Oh, I modified, I think, this diagram only. Right. So now the next focus is on this load side. Load side in this way. So far we had concentrated on the source side. Now let me concentrate on the load side first. Then we go with some kind of little analysis way. So now load side, I'll write as like this. Now try to observe that R phase load is ZR. What is ZR is impedance of the R phase. We know that impedance can be like a complex number. It is a complex number. Complex number. It may be R plus JXL form or R minus JXC form. It may be either of that. If it is RL combination, R plus JXL. If it is RC combination, R minus JXC form. So which may be in generally can be written as A plus JB form. Similarly, the other corresponding thing Y phase and B phase loads are ZY and ZB. Now here I want to point out one important thing, that balanced load and unbalanced load. Balanced load and unbalanced load. Unbalanced load. Just like balanced source and unbalanced source, here also we have this category. Now how we classify this is that based on the impedances of the each phase. That is, this is a complex impedance, so which can be written as magnitude mod ZR at an angle of theta R. Theta R phase angle. Similarly, mod ZY at an angle of theta Y. The theta Y may be negative, positive, it doesn't matter for us. So similarly, ZB is equal to mod ZB at an angle of theta B. Just whatever these complex numbers are there, I am trying to put up in the polar form. That's only the difference. Now see that, or actually let me include these things over here. Over here. So these are general things, so I am putting over here. So I'm trying to make the impedances into polar form in this way. Now based on this polar form notation, it is easy to classify this balanced and unbalanced. So one thing is that magnitudes must be equal, whereas balanced source also magnitudes are equal. So ZR is equal to ZY is equal to ZB. And not only this condition, other condition is that angles of these impedances theta r must be equal to theta y, it must be equal to theta b. If these two conditions are satisfied, then we can say it is a balanced load. It is a balanced load. Try to understand the difference between balanced source and balanced load. In case of balanced source, we are looking for the voltages and its magnitudes. Here, impedances and its magnitudes. Their voltage angles must be differed by 120. Here, angles must be same. Which angles? Impedance angles. So, quantities are different. Try to observe. This is balanced. Now, if it fails to satisfy this condition at any form, in any form, as ZR is not equal to ZY, then it is unbalanced. So, if it does not, it, it does not satisfy balanced condition, balanced condition. Just there are many combinations out of this, that's why I'm not writing all those things, but just as an example I can put up like this. In case if ZR magnitude is not equal to ZY but remaining all are satisfying, so these are not equal, then it is unbalanced. If all are not equal, then unbalanced. If angles are not equal, unbalanced. Any one of these condition failed, then it is unbalanced, like that. So now with this unbalanced loads or balanced loads, so means basic understanding of the balanced and unbalanced. Now I can move on to the let me say in this way. Just try to understand this diagram little bit in this way. Now the configuration can be, let us assume that all are balanced. What are they? Source and load. source and load. Next is one more important configuration, that so there may be neutral connection or there may not be any neutral connection joint between the source and load. So this is the additional thing. So first what we do is that we will take up the, let us say, four wire system, four wire system. Four wire system is nothing but, now I should I should uh, add I should add the neutral wire also through the lines. Now try to observe that in the lines how many wires are there? Four wires are there. So this we call as four wire system. Four wire system. Four wires, what are they? What are they? R phase line, Y phase line, B phase line, and neutral line, and neutral line. And here neutral does not have any impedance also. This condition also emphasized. This condition also emphasized. Now here there will be some objectives on this diagram for us. So let me take this diagram again. So this is important for us in analyzing the next configuration. I will take one by one. So this is one of the configuration. So I introduce later some other configurations also. So I am not listing out all those configuration first, then one by one. Just I want to show you. So based on the necessity that we may go with different configurations. First thing is four wire, four wire, four wire system, four wire system. So you should understand that four wire system means neutral connection also existing, and in which just I am considering the important thing is that Zn, Zn is nothing but neutral impedance. Let me put up these things. So these are assumptions. So let neutral impedance, neutral impedance is equal to 0. So neutral impedance I am considering as 0. What does it mean is that here there is no impedance. Here generally we can assume some impedance, but this impedance is not there. It is a 0. That is one way. Or you can consider in another way that there may be impedance just like this phase impedance. Here also you may see some impedance. So that also not there. So this is one of the important assumption that neutral impedance is 0. With this, we will analyze this. The objective is finding. So finding. Let me write. What we want to analyze in this diagram is that we want to finding the line currents, finding the line currents and 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 neutral current, and neutral current, neutral current, right? So neutral current I did not indicate it. Let me indicate the neutral current here. So one simple observation you should make here, that the R phase current is flowing in this way, and it is passing through the R phase load. Then where does it go? It reach to the common terminal, and it is coming back to the source through the neutral. Similarly, Y phase current also flowing in this way through the line, and through this line internal load, and through the Y phase load, and reaching to the neutral. Where does it go? It go through the neutral in reverse to the source. Similarly, B phase current is passing through the B phase source and to the load in this way, and it reach to the neutral. Then where does it go? After reaching to the neutral, it go through the neutral wire. So this entire current will we will refer as in, but the direction of this in is opposite to the line currents. Try to observe, line currents are from source to load, neutral current is load to source. This you must make important observation, and this I am referring as I capital N. I capital N. Neutral current is I capital N. Right. So now, to get this objective, that is finding the line currents and neutral currents, what I will do is as like this. First, try to assume the system. So how we assume the system? Let source and load e loads are balanced. You should understand what is balanced means. Next, further, let er, that is the source voltage, is equal to E at an angle of 0. Once we know this, we can predict remaining two. What are they? Ey is equal to E at an angle minus 120. All of you write along with me these things. And Eb is equal to phasors. Everything is phasor. E at an angle of minus 240. These are phase voltages. Once we know the phase voltages, we can write up the line voltages. But as of now, line voltages are not required. So here, but just I want to write why, because it gives the practice which will be helpful for the next case. Here it is not required the line voltages, but I am writing those line voltages for your practice, like ERY is equal to E at an angle of, sorry, root 3 E at an angle of 30 degrees. Are you understanding? EYB is equal to root 3 E at an angle of, tell me, 90 degrees. You add for this root 3 at an angle 30 degrees for above phase voltages. So root 3 is multiplied, angle will be added to this angle, so you will get. Then BR is equal to root 3 E at an angle of, tell me, minus 210 or plus 150. It's your wish. Hmm? So that's what I'm saying. Or it is root 3 E plus 150. Right? If this is or E at an angle of 120 plus 120, so you can get this way. So this phase line voltages as of now it's not required, but we produce these things. Next is, you should observe the diagram very carefully. So let me take some portion of the diagram that gives you important observation, that what I am considering is, observe that only R phase and neutral wire through this combination. Try to observe carefully. That I want to put up over here. Means I am considering part of the system. So for your understanding, part of the system in this way. See here, part of the system. Now try to observe carefully. What is the voltage across the R phase? That is, let me say this is R terminal R line and N. What is the voltage between R and N? What is the voltage between R and N? ER? Yes or no? Can you hear me? Hello. What is the voltage between R and N? R and N voltage is ER. Okay? Fine. Next, as because here impedance is not there, so the voltage across R and N is ER. That is should be clear for everybody. Next is the same voltage will be applied across the ZR. Try to observe. So I am writing that conclusion here that VR is the load voltage is equal to source voltage ER. Can you get the point? Just what I am trying to see here is that I want the load voltage, thereby I can write the current through the load, where current through the load is IR, which is the line current, which is IRL, obviously. Is this clear for everyone? This how I written? Simple parallel combination. That the source and load is in parallel. Source voltage is ER means load voltage also must be ER. That's why VR is equal to ER. Can you understand this statement? Is there any difficulty? No. Nobody is speaking. Why? I will not find. Voice is breaking. Now is it okay? Yeah. So, is there any doubt in this? Is VR equal to ER, that is okay or not for you? Are you convinced with that? All of you. All of you. Yeah. So, this is a simple KVL equation. If somebody want in this way also you can think. So let me put up the thing as like this. Let me start here. Let me start here and move in clockwise along the dotted lines. You add up all the voltages in this path, you will get your required thing. I reached again the starting point. So if I am traveling from here, is there any voltage in this line? Line voltage is 0. Why? Because this is conductor. Conductor, does it have any resistance? No. Ideally speaking, no resistance. Up to this, no voltage drop. Here there is impedance. That means there is voltage. So what is its value? VR. This is plus, other side is minus. So you can write in this way KVL. Plus VR. Next, move on further. Here only simple bare conductor is there, no voltage drop. Up to this no voltage drop. Here, could you see ER voltage? So that is minus ER is equal to 0. Of course, we should take the phasors. So this is what the KVL for the above loop, one of the phase loop. So based on this, we are getting VR is equal to ER. That is simple thing. Like parallel combination, parallel elements have same voltage. That basic idea I had written over here. Okay. Always this is our approach. First we will look for the source voltage. Then we will look for the voltage across the load, then we will look for the current through the load. Let me write now current through the load as IRL. Why? Because the same line current is flowing. IRL is equal to voltage across this load. How much? VR. How much is VR? ER. So I can write VR phasor divided by ZR. ZR. So as because we assumed the balance load somewhere I had written here. Let me put up the load values as ZR. So as like this. So ZR is equal to ZY is equal to ZB is equal to Z at an angle theta. So this is a balanced load. Balanced load. So now I can write ZR is equal to, in this way, this is ER phasor divided by Z at an angle theta. ER is E at an angle 0 divided by Z at an angle theta, which is equal to E by Z magnitude, angle is minus theta. Got it? This is phasor, ERL phasor. Similarly, you can try for the Y phase corresponding thing. Let me select that. So Y phase corresponding things, and the neutral, and the neutral. So now again think of the things carefully. This extra things came. Yeah. So now see that. Now Vy is equal to Ey. Let me write directly from the KVL. So let me put up the path also. Start here and just move on through this path and write down the KVL. You will get. So if you write down the KVL for this portion, Vy phasor is equal to Ey, and Ey we know is E at an angle of minus 120. I am writing now directly. And once we know this, the IYL current is equal to Vy phasor divided by Zy. We know Zy is equal to Z at an angle theta, and this can be written as E minus 120 divided by Z at an angle theta, which is equal to E by Z magnitude, angle is minus 120 minus theta. Similarly, you can choose the other phase. Other phase is B phase. B phase corresponding thing, and the neutral. So what we get is as like this, and now let me remove the Y phase. Then think of again the KVL, etc., all those things, and try to write down the equations. So let me write directly here. And VB is equal to EB is equal to, you can write E at an angle of 150, and IBL is equal to VB divided by ZB is equal to E at an angle of 150 divided by Z at an angle of theta. So this is equal to E by Z at an angle of 150 minus theta. So if you combine all these diagrams again, once we know these quantities, so why we split it into individual loops is that R phase and neutral, Y phase and neutral, B phase and neutral is to get the line currents through the loads. The line currents are same as that of the load current. So we got the line currents. That what is our aim. Next aim is neutral current. How can I get the neutral current? Check it here. If I'll write the KCL over here at the load neutral terminal small n, entering currents is equal to leaving currents. So I capital N is equal to IR plus IY plus IB. So I'm writing that corresponding equation. Now referring to that diagram, so let me write here. So KCL at node small n, at node small n. What does it give? In is equal to phasor sum of the line currents is same as that of the load current. So IRL, IYL, IBL. Now you substitute and simplify all these things. You will get one interesting conclusion. So all magnitudes are same. So I am just, if you want, you take your own time and write down later on. I'll directly write this in this way. E by Z is the magnitude for every current. I'll take that common. What left is 1 at an angle of 0, not 0, minus theta, plus 1 at an angle of minus 120 minus theta. Next, plus 1 at an angle of 150 minus theta. So now you write down this into like sine and cosine forms, or or so let us assume some angle for simplicity. It doesn't matter what will be the angle theta. So let theta is equal to 0, or theta is equal to some 30 degrees, or theta is equal to minus 30 degrees. Any angle you choose. So you will realize that this for 0, this is 1 at an angle 0. Let me write here E by Z. All of you calculate this. 0 plus 1 at an angle 120 minus 120 plus 1 at an angle 150. How much is this value? Can you tell me? 1 at an angle 0 plus 1 at an angle minus 120 plus 1 at an angle 150. Quickly. It is equal to 0. Observe carefully. 0.5? No. Check it properly. It is equal to 0. No, no, this is not 150, no? Why we took 150? B phase is not 150. That is what the mistake. That might be the reason you are getting. So nobody is pointing out. Means you all are not listening class. B phase voltage is how much? Minus 240 or plus 120? These are phase voltages, not line voltages. So plus 120 I am considering. Plus 120 minus theta. All of you make this change. B phase voltage is E at an angle of plus 120. This one. Where it gone? Yeah, this one. So don't consider 150. That may be wrong. Why? Because that is line voltage angle. So here you have to make the change that this is 120. This is also 120. Now you check it. It is 0. Yeah, yeah. It is 0. Yes. So, sorry, not 0. This is 0. Similarly, even if you put 30 degrees, it goes 0. You can check if you want. Even if for 30 degrees also 0, even if it is minus 30 degrees also 0. For all these three cases, or any theta, for any theta, this will be 0. For any theta, this will be 0. For for any theta value in is equal to 0. What is the conclusion from this point is that if source is balanced and load is balanced, there will not be any neutral current through the neutral wire. This is the very important conclusion. So let me write here for balanced system. I won't write individually, just I am writing directly. Balanced system. That means balanced source and balanced load. The neutral current is 0. Is 0. This is very important conclusion. For balanced system, the neutral current is 0. So now I would like to give one simple task. The task is in this way. The same diagram, four wire system, but little modification. Here, this four wire system does not have any impedance. Try to observe that. Neutral impedance is 0. Now, what I want to do is that same four wire system. Let me copy up to this. But now neutral impedance is not 0. Neutral impedance is not 0. Now you should work out this case. So I'll give the clue and you can take up this problem forward and you can work out on this. This is the thing. And now the let us say in this case 2, four wire case 1 and case 2. So in case 2, this is very very important, this case 2 problem. So let me remove here small portion. And now I would like to add up a small impedance. So I am calling this as Zn, neutral impedance. Now neutral impedance is not 0. For this case we need to work out. Then how we work out is that again you have to take up individual. These all assumptions are same, that load is balanced, source is balanced, no change. And again the objective is also same. So let me copy almost up to this portion. Objective is same. This entire thing is the same. The diagram also more or less the same. Slight modification. I will show that modification also. So see that objective is again finding the line currents and neutral current, and the source and load are balanced. Then source voltages can be in this way and balanced load impedances are in this way. What extra change is that here there is an load neutral impedance Zn. Now if we write the KVL what kind of equation we get? What kind of equation we get? See this. Again, same loop. So first I'll get plus VR. Everything is in phasor form. Then after VR, you move on through this neutral line, and neutral current is IN, which is the sum of these currents, obviously IR, IY, IB. So I'll write this as plus IN into Zn, IN into Zn minus ER, minus ER is equal to 0. Obviously, all are phasors, currents and voltages. And from this, or let us assume this is some equation 1. Similarly, you write for remaining phases these loops, like Y loop with neutral impedance here and B loop with neutral impedance here, KVL equations as the same like this, as like this. Then after getting those, you write that IN is equal to IN is equal to IR plus IY plus IB. So you have 4 equations and 4 unknowns. Now you can solve the required things. Just let me produce the other equations also here. Plus Vy plus In into Zn minus Ey is equal to 0. This is for Y corresponding loop. You will get this equation. Let me write the other thing. Plus Vb plus In into Zn minus Eb is equal to 0. You will get this for the B phase loop. I request everyone to draw that corresponding loops and make a note of these equations, and try to observe that you have 4 unknowns and 4 equations. Think of how to get some important thing that or yeah. So ultimately what we need is this one. Just let me put up that. So neutral current is flowing through this wire. So this side is plus, this side is minus. That is what the neutral voltage. So neutral voltage Vn is equal to In into Zn. This what we need ultimately. So we try to produce this Vn equation in the next class. But before that, I request you to work out in reaching the Vn. So how to get the Vn value? Not this expression, you will get some other expression, but what I need is that this Vn ultimately I need to calculate. When I can calculate Vn is once I know the In. So what is In? Once I know the line currents. What are the line currents? Then I should know the load voltages. Then what are the load voltages? Load voltage is phase voltage minus neutral voltage, phase voltage minus neutral voltage. So in this way you have to do many things. So all are interlinked. So try to complete this portion, and we see in the next class this part of the discussion, and we move to the other configurations. Now today we had discussed so balanced load concept. This one. So balanced load is nothing but impedance magnitudes must be equal and angles also must be equal in each phase of the load. Then we were seeing different configurations of this three phase system, how the connections will be. One configuration is the 4 wire. This is, let me say, 1, and in which case 1 is the impedance Zn is equal to 0. So for this case, we calculated our objective is line currents and neutral current. Once we know this, we can even calculate remaining things. That's why we derived that. Now we got a conclusion that neutral current is 0 for a balanced system with neutral impedance 0. With neutral impedance 0. Try to understand. And even of course neutral impedance is not equal to 0, you will get for balanced system neutral current is 0. So next configuration is that neutral impedance is not equal to 0, then we look for the things. So with this I will close the session.